All right, welcome to electricity part two. We'll start off with just talking very quickly about the cost of electricity. It might be a good little applied question that you'll run across. Now, what are you paying for when you're using electricity? Well, you're paying for the energy. So we know that power is equal to work over time or energy over time, if you want to be lazy about it. And so energy equals power times time. We also know that power is potential difference times current. So if you put those equations together, you get that energy is equal to current times potential difference times time. Now, what kind of units would that give you? Well, it gives you joules, but for our case here, we're going to look at it as power times time. So when you're paying for it, you're usually talking about kilowatt hours. So you have to make some conversion. Kilowatt, so you got to multiply by 1,000. And also for hours, you got to multiply by 3,600. So you get a conversion rate of 3.6 times 10 to the 6 joules. Not sure what the costs are here in Japan, but for example, in Hong Kong, it was 1.3 Hong Kong dollars per kilowatt hour. So that's the kind of rate that they'll show you. Circuits is what we're going to focus on. Just remember all the little diagrams. Look it up in your formula booklet. Now, as far as circuits go, a few things to look at. One is a series circuit. So there's an example of one. What I mean by a series circuit is you can put resistors or other elements in your circuit one after the other. Now, if you look at this, it means that the current has no choice. It must go through the resistors. It doesn't split off and kind of choose which one it goes through. That makes it in series. This can apply to resistors, but it could also apply to cells, which actually is what you're looking at here. It's two cells making a battery. Okay, so you can also have the same thing for them. Now, the way this works is that the total potential difference gain through the cell, or the electromotive force, must be equal to the loss of energy per unit of charge. In other words, the difference in the lowering of the potential difference, one resistor after another. So when it drops across the first resistor, then it drops across the second resistor, and then it'll drop across the third resistor. That must be equal to what the total gain was in the cell. So you look at this equation, the total potential difference is equal to the sum of all three drops. If the potential difference is equal to current times resistance, you can replace that. Notice that the current is all the same. That's because there's only one path for the current to go through. So it's all the same, therefore we can divide both sides by I, leaving you with this nifty little equation for how you calculate total resistance in a circuit. If it's in series, you simply add up all the resistors. Okay. It's a different story with parallel circuits. With a parallel circuit, that means that when you're kind of going through here, the current will split, and so some of the current will flow through one resistor, and some of the current will flow through another resistor. And you can make a circuit, you can make a loop going through one of the resistors or the other, but not both. And in this case, it's an example with three paths. So those are parallel circuits. And the way we look at that is we use Kirchhoff's law. More on that in a slide or two. And what it tells you, it's very logical. The current that kind of flowing from the battery at this junction splits into two. So some of the current will flow through this resistor, some of the current will flow this way, and then in this case, since there's three resistors, it will split again. Some of the current will flow through this one, and some of the current will flow through this third one. How much current flows through each path depends on the resistance. Okay? But the total resistance must be equal to the sum of all the paths, current. So current is equal to potential difference divided by the resistance. So it would be this. Now in this case, notice that the potential difference is always the same because if you go from here through this path to here, the potential drop across the resistor will be exactly equal to the potential gain in the battery. And if you go through this path, it would be the same story. And through this path, same story. No matter what, let's say this is 6 volts, it would have to drop 6 volts across here and come back here. Or same story here, drop 6 volts back here. Okay? So in this case, you can divide both sides of this equation by V, leaving you with this equation. And so that gives you a way to find the total resistance given 3 resistors in parallel. So if it was 2, you just knock this one out. Now be very careful about this. When you do this, look at the right side. You can calculate that, but don't forget on the left side it's 1 over total resistance, which means that don't forget to find the reciprocal of the right side in order to find the actual resistance. If you do this calculation, you'll notice one thing. With parallel circuits, if you add resistors in parallel, the total resistance actually goes down. For example, if these are all 1 ohm resistors, here you would have 1 plus 1 plus 1 equals 1 over total resistance. So you get 1 over total resistance equals 3. Therefore, the total resistance is now 1/3. And that kind of makes sense because now the electrons have more paths to go through. So it therefore makes it easier for them, not so crowded. They're not forced to go through all this, through the same wire, through the same resistor. If you go back to series circuits, that's not the same story. The resistance would increase as you add resistors in series. Now, a bit more about Kirchhoff's laws. There's 2 laws here, the junction rule and the loop rule. Now, the junction rule, I've mentioned it, and I'll mention it again here, that if current is flowing through a circuit and there is a junction, a place where the current splits, the current going into that junction must be equal to the current going out of that junction. So in this case, if you want to call this current 1 and this current 4 or something like that, and then this is the total current coming at it, the total current would be equal to current 1 plus current 4. Okay? And here, again, the same story. Current 4 would be equal to current 2 plus current 3. Okay? And then when they join back up, same story. They would join up, make this current. These 2 currents here would add up to make this total current again. Okay, so at any junction, you can calculate that. Very handy for calculations. The second Kirchhoff's law is the loop rule. In any closed loop in a circuit, the sum of the electromotive force equals to the sum of the potential drops. Okay, now again, I mentioned that. So if I look at this, through this loop, any gain in potential through the EMF, the battery, must be equal to the drop in potential across all the resistors in that loop. Okay, it applies to any circuit, so you have the same thing here. Say you gain 6 volts here, you would have to lose 6 volts here because it's a single loop. Same for this loop, and same for this third loop. Okay. The interesting thing is you can even run these Kirchhoff's law in little loops like this, which doesn't even have an EMF. The thing is, if you're kind of saying, well, the current's flowing through here, this would be a potential drop. And if I'm going through this loop, this would be a negative potential drop. So in other words, it becomes positive. So say you go negative 6 volts here. Since I'm going in the reverse direction, this would be plus 6 volts, and it adds up to 0. Right? They got to be equal to each other. So it's kind of an interesting little kind of way to handle that. How do you measure current and potential difference? With an ammeter and voltmeter. Okay, they're essentially the same devices. More on that when we talk about magnetism, because they use magnetic principle of current flow. And the only difference between them is that the ammeter has virtually no resistance in it, and the voltmeter, they put a massive resistor in it. And I'll explain why, but they are the same thing. the general device is called a galvanometer. Okay. If we take a look at the simplest circuit possible, the ammeter must be placed in series. So you must actually integrate it within your circuit to measure the flow of current through that point. Okay. If you do that, remember this thing has almost no resistance, so therefore it would make little difference to your overall circuit. That's the whole idea. So it measures the flow, but there's so little resistance, it doesn't change the actual circuit itself. So you can put it here or anywhere else. Okay. So if I go back to a parallel circuit, if I put an ammeter here, I get the total resistance. Sorry, the total current. If I put it here, I get the current going through resistor 1. Here, the current going through resistor 2, and here, the current going through resistor 3. If it's in series like this, it actually doesn't matter where I put the ammeter, it would read the same current because it's all flowing through the same loop. Okay? For the voltmeter, okay, you have to actually connect it as in parallel. And because what you're doing is you're comparing it 2 points on your circuit. Now this thing has such a massive resistance that by putting it in parallel, very little current would actually go through the voltmeter. There's enough to make the reading, but not enough to change your circuit. So it's in parallel, yet its resistance is so big that it becomes essentially not part of your circuit. So if you look back at the parallel circuits thing, it's as if you had this here, this resistance was so big, this becomes 0. So it has no effect. Okay? So the voltmeter must be like this. And you put it on either side of the thing you want to see the potential drop. So if you're interested in this resistor, you put the voltmeter on either side. If you're interested in the cell, you'd put it on either side of that. In this case, since there's nothing between this point and this point, and there's nothing between this point and all the way over here, there's essentially no resistance, they would read the same, which makes sense. Any potential difference gain must be equal to any potential difference drop. Okay. If it's in series though, here if I put the voltmeter and I put the point here and here, then I would read the potential difference in the battery. But if I move it here to here, I would measure the potential difference of resistor 3 only. And here, resistor 2, and here, resistor 1. Okay? One more thing, we saw this last class. It was just mentioned. I said, well, we'll talk about it in a bit. A potential divider. It's a little system. It's a little setup that you can have in a circuit to reduce the potential difference in your circuit. So this is the way it works. You can put here at this point and at this point, between these 2 points, you can put in a battery or something. Let's say it's 12 volts. Okay, so it completes this circuit. Now you put in 2 resistors like this. And what you do is you add a little wire here, and now if you connect anything between this point and this point, okay, you'll get a different potential difference than you would have between this point and this point. Okay, so think about it. If it's this, let's say that this is a 12 volt potential gain. There's a battery here. It would flow through these 2 resistors. Let's say each resistor, there's a resistance of, I don't know, 1 ohm each. Okay. What would that do? Well, first of all, the total resistance is 2 ohms. Therefore, the current would be 12 divided by 2, so 6 amps. Okay. So therefore, the potential difference here would be current divided by resistance, so 6 divided by 1, so it's a 6 volt drop, and here the same thing, 6 volt drop. So again, let's go through that again. This is a 12 volt gain in EMF, goes through here, there's a 6 volt drop here, and there's a 6 volt drop here. So think about that. If you put something here in parallel to resistor 2, it would have the same potential drop as resistor 2. So therefore, you would get here a 6 volt difference here. So you can connect a little something that needs 6 volts, and there you have it. The trick is you got to make these resistors fairly small compared to this one. Otherwise, it'll change your circuit too much, and therefore you're going to get a different potential difference across here. But it's possible to do it. Okay, you can put in kind of constant resistors like I mentioned, or you can put in a rheostat, which is a fancy word for a variable resistor. Right, okay. Don't forget about that electromotive force. I've mentioned it before, but don't forget it's the same thing as a potential difference gain. And there might be questions where they mention that the internal resistance. Okay, so don't forget about that. In your equation, your formula booklet, the big R is your total resistance. The lowercase r is your internal resistance inside the cell. Remember, a battery will heat up. Okay, so that means there's resistance in there. Any questions? Well, I can't answer them because this is a recording. But I do have a question for you. Here's a nice, fairly complicated little circuit. Okay, but it's a great one to start practicing and using our rules. So we have to kind of figure out all the resistance, current, potential difference, and power across all these resistors. So and the totals. So how do you tackle that? Well, if you look at any of these resistors, you only have one piece of information each, so you can't really solve anything there. Okay. The 12 volts here, you have that piece of information for this battery, but you don't have the resistance and you don't have the current. So it kind of leaves you with very little to work with. But you could figure out the total resistance of the whole system and therefore start to figure out, well, what's the total current for the whole thing? So let's figure out the total resistance of this. First of all, I look at this, and if I follow along, I see there's one resistor in series, and then these two resistors, 1 and 2, are parallel to each other. So what I'm going to do is break up the problem into 2 parts. I'm going to figure out the resistance of these two that are in parallel. So I'm going to use this rule for parallel resistors, and I get the total resistance of these two. With that, I'm going to add that answer with the 470 ohm resistor that's in series. Therefore, give me the total resistance of the whole thing. Once I know that, I know the total EMF gain, 12 volts, so I can figure out the total current flowing through this. Okay, so I just do that. Current is potential difference divided by resistance. Make the calculation. I get a very small 0.0218 amps. Okay, that's my total current going through, okay, the battery. So once I know that, take a look. That current flowing through will actually be the exact same current that flows through here. It does not split at any place between the battery and this resistor. So I can use that current in here to figure out the potential drop here. So I'll do that. And I get 10.2 volts, a potential drop here. Now if you think about it, now we can use Kirchhoff's loop law and take a look. 12 volt gain, 10.2 volt drop. Therefore, if I follow through in this loop, it must drop another 1.78, depends if you're rounding off, 1.8 ohm drop across this resistor. So I know now the potential difference here. I know the resistance, therefore I can figure out the current going through here, which is a very measly 0.00808 amps. Once I know that, I can use, well, you have a couple of choices here. The potential drop here must be the same as the potential drop here. Think about it, look at this loop, right? You know, it gained 12 volts, lost 10.8 here. It must lose, again, the same amount, 1.78, to get back here, okay? But you can also use Kirchhoff's law at the junction here, and you know how much current is going into it. You know how much current is going this way. Therefore, you can easily calculate how much current is going through here. And that's what I ended up doing here. Okay? Either way, you'll get the same answer. Once you have that information, I think it's fairly elementary to figure out the power for all this, because power is simply current times potential difference, and you have that information on each one now. So I'll let you figure that out. I ran out of room. Okay. So again, if you want the answers, here they are. So that's a nice little example, but ultimately it's up to you to do those problems in the textbook and practice this stuff. So hope you enjoyed.